video, we're going to be looking at population of a city. We're going to be modeling our exponential skills. Since population usually grows or decreases exponentially, we're going to be looking at how these things come together. So the population of a large city was about 4.6 million. So 4.6 million in 2010. So 2010 is going to be our year zero. This is the initial year that we're going to start monitoring population growth. We have no data from previous years, so this is why this is our initial. I mean, I'm sure we do, but in this example, we don't. So we're going to start with 2010. And the population they found grew at a rate of 1.3%. All right, so we're growing, we're not decreasing. So what is the exponential function model of the population of the city at a 4-year period? So we need to first come up with a model. So the first thing I'm going to look at year zero, this is year, this is population. At year zero, we had 4.6 million. At year one, we're going to have that 4.6 that we had the previous year, and we're going to add the people who came about, which is the 1.3%. 1.3% of the babies. I can rewrite this as 4.6, pull out a greatest common factor. Remember, 4.6 is being multiplied to 1, so I'm left with 1 when I pull out 4.6, plus 0.013, or 4.6 times 1.013. All right, so the year after, well, that's year 2. We have a 4.6, the population from before, 1.013. And we're going to be multiplying this by, again, the new babies that came, 1.013. So 100% of the population plus the babies. So this is 4.6 times 1.013 squared. And we're going to keep doing that. And what you're going to find is you're going to find a function, a population function, equaling to the initial population, or the population you start out with, times the rate at which the population grows or decreases. So if it's a growth, R is going to be greater than 1. If it's a decrease, R is going to be less than 1, but greater than 0. All right, and then this is to the t for the time that we are going through. All right, so if I'm looking at this setup, we have P of x, or I like how I put P of x and I put a t there. P of t is equal to the initial population, which is 4.6 million. Any math, anything that we do on this will be in the millions. My rate is 1.013 to the t power. So in population, it's usually 1 plus for growth. So you're looking at 1 plus that rate that they're giving you, and this one is 1 minus the rate that they're giving you. And so we need to look at it at 4 years. So this is P of 4 is going to equal 4.6 times 1.013 to the 4th power, or I thought I had my calculator up and ready. So we're just going to try this on my phone calculator. So 4.6 times 1.013 to the 4th power. I get 4.84 million people. So part 2, if the population continues to grow at the same rate, what will the population be at 2040? Well, see, we start at 2010, we're going to 2040. We have our function, so our population of t equals 4.6 times 1.013. And if we start at 2010, so at 2010, this is year 0. 2040 is 30 years from 2010. So this will be 30. And so my answer is going to be roughly 6.76 million people. So in 2040, the population will be roughly 6.78 million. A nice big population, much bigger than where we are, but there you go. So remember the function here for population is usually P of t equals P naught times your rate, which is 1 plus your rate for growth. For decreasing is 1 minus your rate. So this one's growth. And this is decrease. And there you have it. The population using exponentials. And always remember to transform your percentages into decimals for easier use of calculations. I will see you guys in the next video. If you have any questions, please feel free to ask. And I will see you again.